Okay, thanks for coming. My name's Tom Enebo. I'm normally known as Tom and not Thomas, but I always feel I need to be formal. As Sarah said, I'm a JRuby co-lead, and I'll also point out that Charlie and I are doing a JRuby talk after lunch. I don't have the details on the screen, but I should have put that there. I've been using Ruby and Java a very long time. I'm also kind of a fan of Rust now. And if you're an employer looking to hire me, I'm looking for a job. So here's my LinkedIn link. All right, so what's an esoteric programming language? Wikipedia has a lot to say, but we're not going to read that. All right, I'm going to break it down to 2 sentences. It's a programming language that's typically hard to use or understand, and you're going to consider the language weird in comparison to a traditional programming language. The language we're going to be looking at today is Piet. It's named after this guy. There's one of his more famous pieces on the right. He unfortunately didn't have a great fashion sense later in life. So we'll remember him by this photo. He's pretty cool. He's somewhere between George Clinton and time-traveling hipster. And if you want to go and waste 5 or 10 minutes of your life, but be somewhat entertained, look up time-traveling hipster. Narrator, he's not a time traveler. So Piet's an image-based language, just like Smalltalk. Well, no, not really. It's literally an image. So if you run Piet on this image, it's going to display Piet to the screen. It's also a funge. Funge is just languages that involve coordinate systems. It's stack-based. The primary unit of things is a codal. This is n by n set of pixels. This one is 10 by 10. Adjacent codals are made into groups. So in the upper left-hand corner, we have a 3 by 3 group. There's a direction pointer. This indicates the flow of the program as it moves through the image. All Piet programs start by executing in the upper left-hand corner of the image, and it is set to write initially. There's another concept called a codal chooser, where it's either set to left or right. And so the navigation is the direction pointer will move through a group and try to enter the next group. And at the most extreme edge, the codal chooser will say, should I go at the left side or the right side of that edge? So here's just a visual representation. If the direction pointer is right, the codal chooser is left, we're going to go from the blue to the dark blue square group at A. But if the codal chooser is right, we're just going to go in on B. It's pretty simple. Okay, harder example. If the direction pointer is right and the codal chooser is left, we're going to go and enter into this green group. But had it been right, it's going to go into this dark blue group. Piet programs have 6 different colors, and each of those colors have 3 different shades: light, normal, and dark. And when you transition from one group to the next group, you go and reference this table to figure out what operation to perform. We have some stack operations. We have math, inequalities, input and output. And then we have 2 special operations. One is pointer, which allows you to programmatically change the direction pointer, and switch is the same thing for the codal chooser. So when I say one shade darker, and this is how it's written in the Piet spec, it makes sense that light blue to blue is one shade darker and blue to dark blue is one shade. But it also is that a dark blue to light blue is one shade darker. So don't get too hung up on the word. It's just a circle. Similarly for hue changes, again, it's just a circle. All these are examples of the divide operation. But if you go to red, you just go around the circle too, and that's it. That's green. Okay, so now we're just going to go through a program to get an idea of how it works in practice. So as I said, we start in the upper left-hand corner because the direction pointer is right, curl chooser is left. So we enter into the dark blue group at that upper point where the arrow is. And we look it up. It's one shade darker. So we're going to do a push. And we're going to end up pushing 9 because we use the size of the group that we're leaving as the value to push. Okay, so now at step 2, we run into black. It's not one of the 6 colors. It's an impassable color. In fact, if you actually exit off the side of the image, it's equivalent to running into black. So you can just kind of pretend all Piet programs are just lined with a black border. And so when this happens, you do this algorithm. So for up to 8 times, you flip between the curl chooser and you just rotate the direction pointer clockwise and try to find another place to go. If you can't find it in 8 moves, that's how a Piet program terminates. Okay, so curl chooser goes from left to right, and we move in and we're off to the races. We're still executing. Okay, we'll go to the next special thing. We're now in this little L-shaped green group, and we're moving down. And I promise you, that is white. It does not look white, but for the sake of this talk, it is really white. In the case of white, though, you just kind of slide through to the next thing. All right, so that's the basic rules of Piet. And I'm sure everyone's going to run off and make their own programs. If you want to run them, you can go and install Rpiet. This is my implementation of the Piet language. It will run in C Ruby or JRuby, but if you want to use the graphical debugger, then you have to use JRuby. And that's using a JRuby library called JavaFX, which is pretty sweet. Okay, so a few example programs to kind of whet the appetite for writing your own Piet programs. The first one is Cause. I am just executing this off the internet. And when you run it, it prompts you for some text, and then the cow goes and repeats it. It's pretty cute. This one's kind of mind-blowing. Someone figured out how to go and make 2 programs in one image by changing the codal size. So it just prints 2 different things. This is my favorite. As I say, you enter a Piet program by going to the upper left-hand corner. The first thing you hit is this red line, which is half the image's size. So you push that onto the stack. Then you go and find the circle, and you push that, and that's the area of the circle. Area over r squared, right? And you get this perfect pi number. So I should point out that there are no floating point in Piet. So pretend there's a period there. But this is actually a better approximation than at least one state's legal definition of pi. So there's that. Okay, so now I'm done talking about Piet the language. I'm going to talk about implementing it myself. I just ported it from Python. Yeah, so porting's hard. Python and Ruby are not identical languages, so there's different idioms. Porting code, you make lots of stupid mistakes where you just do the wrong thing. And there were no tests. I say few tests, but there were none. So what you do is you generate a debugging output that's similar to another Piet implementation, figure out what's wrong, and then fix it. I was comparing against Rpiet, which is kind of the best Piet implementation, at least for now. Okay, so I made a graphical debugger, so let's take a look at that. All right, so I'm going to start by hitting step oh wait, I gotta start it though. All right. So I hit step once, I hit step again. Now I'm gonna go and set a breakpoint, then I'll resume. That gets there pretty quickly. Then I look at the stack, yeah, that's what I expected. Then I keep running it. You can see it bouncing around. So the fun thing about this video is it gives you the illustration of that I'm going to try to move stuff 8 times and then terminate. So if you look at that green upside down T, it's surrounded by black. And so it did the 8 different changes and then said, I'm out of here. Okay, so I quite literally ported the interpreter. I don't expect you to read that, or I'm not sure if you can even read it, but it's almost all in one method. It's kind of what I call code chowder. There's just way too much stuff in a method. So it has a mixture of concerns. It's continuously reparsing and changing that direction pointer and cold chooser, and that's invariant logic. So we need to fix that. Like the short-lived McDLT, we have to keep the hot side hot and the cold side cold. Does anyone remember McDLT? All right, we got a few people. I thought, you know, sometimes I put this stuff in for me, so. But in all programming languages, you translate the text of your language. I shouldn't say all. Nearly all languages, you translate the text into a data structure. It's almost universally an abstract syntax tree. So here's a snippet of Ruby. When this gets parsed, it'll construct a while node, and then there'll be a Boolean node for the test, and then there'll be a call node with the puts in it, and so forth. Now, in most languages, and Mats even mentioned this in his keynote this morning, the interpreter that you make will actually be attached to this tree. So every one of these nodes will have their own execute method. So when you actually execute a while node, you'll just call execute on the while node. It'll do the test, it'll execute the body, and so forth. So that's what we're going to do now in Rpiet. But it has all sorts of weird abilities to like fold back in on itself. So we can't really do a tree, so we're going to make an abstract syntax graph instead. Every node is going to be the operation we perform. So if you remember in the early examples where we went from blue to dark blue, it was a push. So that we'd create a push node, and pretty much every operation that was in that table will become its own node. We have to create some new nodes to keep track of when the direction pointer and cold chooser changes. So that'll go into the graph as well. And then the algorithm is we're going to just strip out the execution from the original code chowder and make it into a visitor. And for every possible transition from one group to the next group, we're going to add it to a work list. So for the pointer operation, that can potentially go 4 different transitions. So we just add them in there. And we just process this thing until we have a complete graph. And now here's what the graph interpreter looks like. We start at the entry part of the graph, and then I'll just bring the push up again. For that example program, the first thing we'd execute is push, and then when it finishes, it returns the next node to execute. And if it returns nil, program's done. Simple. Okay, so the benchmark for the rest of this is going to be a prime number detector. When you run it, it prompts for a number, and it tells you whether it's a prime or not. And it's got a nice little face on it. And I couldn't think of a number to use, so I'm going back. I'm going way back. 8675309. Does anyone use this number whenever you have to do a fake phone number? Okay, more people than knew the McDLT reference. That's good. This is from the song Jenny. It's her phone number, and it's forever etched in my brain. Okay, so when I run the original interpreter, it takes about 147 seconds, and now with the new graph interpreter, it doubled in speed, effectively getting rid of that constantly reparsing the image to navigate. It's a pretty good payback, so good. But we want to make it faster now. So let's get away from the abstract syntax graph and go to a list of instructions. And these list of instructions will mostly be the same that the operations in the original table. But because we have these weird jumps and flow control changes, we need to actually add branches and jumps. And so now what we're getting to at this point is we're going to convert this graph into a single sequence of text with instructions. So I'm effectively making a simple programming language. Here's a translation from the dupe operation in the graph, where we just take the top element of the stack and duplicate it. And now for the new IR instructions, I'm going to actually make 3 instructions where I pop the top element and I just push it twice for reasons. And so now we end up with a single list of instructions. And this is pretty easy to read. And it's a lot easier than reading a GIF image. So if we look at the green underline here, jump to test end towards the bottom, what that will do is it'll look for the label test to end and execute that instruction next. And if we look at our new interpreter, we now have this instructions list that's indexed with this program counter, and it gets the instruction, it executes it, and if flow control changes, it returns something that we can then use to look up in a jump table for the next index that we should execute from. And if not, it just increments the program counter and does the next instruction. Uh-oh. Well, I did actually add more instructions than there were originally nodes, so I think this is sort of to be expected. And I'm actually trying to massage this in a way where I can do common, well-known optimizations, things that if you'd taken a compiler's class, you would have it in your textbook or you look up on Wikipedia. And I did the dupe thing for a reason for the first optimization, which is to do a simple peephole optimization. So with the peephole optimizations, you take one set of instructions and you look for a pattern that makes it better, generally faster. In this case, I'm using a very specific one. If you see a push followed by a pop, you can eliminate both of those and just make it into an assignment. And you can see here, if there's multiple of them, it's almost kind of like a Russian nesting doll where the push 1, v1 equals pop will just become an assignment. But then once you do that, then you can already see that you can do it again for push 2 and v2. And so now if you can imagine that the next instruction after this is going to be an arithmetic operation, we can do another optimization called constant propagation, where we can just get rid of v1 and v2 and make that math 1 plus 2. And now you're looking at that and you're thinking, why would I do 1 plus 2? I can just constant fold that into a single assignment because I know 1 plus 2 equals 3. And all these optimizations keep stacking on each other. And luckily, Piet uses tons of pushes and pops. So I was able to reduce the number of instructions from 197 down to 76. Now it's 4.5 times faster than the original. It's more than twice as fast as the graph interpreter, so hooray me. Anyone remember Slapchop? Okay, that's more modern. All right, so the last thing that I'm going to do is I'm going to try to get rid of most of the interpreter overhead. As I said, we're constantly accessing stuff out of an array. We're incrementing this program counter, and we're calling execute. I mean, what we're doing here is we're simulating a machine, and that's not very fast. And we're going to solve this by transpiling to Ruby. We still, unfortunately, because of the complexity of the language, have branches and jumps. So we'll still have to emulate the machine a little bit, but everything else can just become transpiled lines of Ruby. And then we get rid of the overhead of that. So I don't expect anyone to read that at all. But for both the optimizations and for this transpiling, I made a control flow graph. The important thing here is you can see all these little lines pointing between boxes. This is all the places where flow changes. And if we zoom in a little bit on one, I gave each one a somewhat random name. I think that 4012 is its object ID. But if we look at how we transpile it, v1 equals n in for numeric input. We just print out prompting for the number, and then we get it from the IO and convert it to an integer. The pushes are pretty obvious what's happening here. And then the very last line is the next method that we have to execute. So now if we look at this version of the interpreter, we're basically just sending to all these generated methods, and they just return the next method to execute. So some people might be wondering, why didn't you just call RE4004 in this method instead of returning it? And it's because we don't have an infinite stack in Ruby. But that would have been way faster if that would have worked. And probably would have worked for a small number of Piet programs. But this was kind of an unexpected thing for me. Once I started transpiling into Ruby, I started getting all these ideas. And like, duh, I've been using Ruby for a couple decades. I know Ruby really well. And I also got to use Profiler, and I was like really surprised that something I thought was fast wasn't fast. So this was an unexpected joy in this. Okay, so now when I did that, now it's 70 times faster. There's other things that I could have done, but I already spent way, way too much time doing this. So I'm going to declare victory right here. But I want to do a couple of conclusions. The first one is I think it's really important to study different languages. So if you're someone who's learning a language and you decide to use a language that isn't very different from yours, you're not going to get a lot of insights. So I recommend like learning a radically different language. I'm not saying you should learn Piet, although you all know Piet now, but learn something like Prolog. Prolog's a declarative logic-based language. It was pretty transformative to me in college when I learned it because I thought everything was going to be like Pascal or C. Pascal might date me a little bit, but yeah, get away from something familiar and don't even spend a ton of time on it. Just spend a few days on it. Just get some appreciation that there's different ways of doing things. I think as time goes on, all the programming languages are starting to look more and more alike. I think this is a pretty good example that when you're in uncertain ground, you just need to translate what you're doing into something familiar. Once I actually made the abstract syntax graph, then I'm like, well, naturally I can make this into instructions. And then once I made it into instructions, there's just tons of things I could do. But when I was looking at that original interpreter, I'm like, I had no ideas on how to improve it. If I would have made it nice and clean, it would have ran way slower. So Ruby and Rails, we have tons of tools. So this isn't as applicable, but Piet had no tools for me, so I had to make everything. So GraphViz was the most useful thing. That control flow graph that I showed, I was constantly looking at those, seeing how my results had changed. And that was super useful. Had I not had that tool, I would have been pretty lost. The graphical debugger I made, it was a total waste of time. But I had a lot of fun writing it, so, take what you can get, right? I had to make an assembler for the IR so I could actually test it. I made an ASCII image format so that I could actually use a text editor to make my Piet programs, because who wants to use Paint or some program like that? But there were many others. And the last and possibly best thing to know is 8675309 is not just a phone number. It's also a prime number. So thank you. Again, looking for work. And I think I have like 4 minutes for questions. If anyone wants to ask questions, I'll answer. Can Piet do anything like change the colors of the program? Now, there are a bunch of people who have extended Piet in weird ways. They've added more colors so they could add more operations. I think someone made like some TCP server somehow. So I wouldn't be surprised if someone made a self-modifying program. So that would be like the ultimate in Lispiness, right? Data is the code, but I'm not aware of that specifically. Can QR codes be Piet programs? Well, it's not one of the 6 colors that do anything, so you could do something with it, but it would just instantly terminate, because if it's black and white, it'll make, well, let's just pretend that there's no border. It would just move around the white, do the 8 thing, and then eventually stop. It might run it might run infinitely, because, oh no, it's gonna stop. Because white just slides through and black's gonna go, nope, it's gonna rotate. Yeah, yeah. Man, we could really go places with Piet. There should be, and another problem I ran into with Piet as an implementation is there's like 20 Piet programs on the planet, and about 8 of them don't do it right. There was errata, and then they updated the Piet spec for something where there's 20 programs on the planet, and so half the programs don't work. And if you use npiet, which is the implementation I was talking about earlier, they actually have a flag to specify, I wanted to use 1.1 of Piet. So yeah, there's at least 3 different versions of Piet now. Okay, well, thank you.
Thank you, Tom.